Emerging from the deep void, faster than the Voyager probes, nearly 36 miles per second, something truly primordial has disrupted the tranquil rhythm of our solar system. Something that defies every cosmic chemistry textbook. This is no ordinary interstellar traveler. It's 3I Atlas. And it has done the impossible. It turned green. An emerald shroud of gas and vapor, a glowing green signature, reveals a cosmic secret forged during the galaxy's earliest and most violent epoch. Conventional wisdom, the belief that the building blocks of life could only have formed in later, metal-rich stellar nurseries, has just been shattered by this relic from a time when the universe was barely a teenager. The so-called green comet effect. Normally the harmless glow of diatomic carbon, here blazes to an impossible degree, hinting at chemical processes we dare not speak of in the daylight. Tonight, under the steady current of the cosmos, deep within hollow Earth, we will trace the billion-year journey of the green enigma. We'll examine the shocking implications of its highly unstable composition and uncover why the color green, far from being reassuring, may be the most urgent warning about its true nature. What if this radiant green glow is not just an astronomical curiosity, but the spectroscopic fingerprint of a phenomenon that could redefine the very origin of life itself? Prepare to descend into the deepest secrets of cosmic creation. The true awakening of the interstellar Comet 3I Atlas's return from its billion-year slumber in the galactic void was not marked by a gentle warming, but by a sudden and spectacular cosmic chemical flare, a bright and unexpected shift toward a vivid emerald green. When 3I Atlas was first detected by the ATLAS Asteroid Terrestrial Impact Last Alert System survey telescope in Chile on July 1, 2025, and confirmed as the third interstellar object ever observed, it initially presented a more typical, slightly reddish. This red tint was characteristic of sunlight scattering off a mixture of dust and perhaps larger grains of material flaking off its former surface. A relatively uneventful start for an object moving at nearly 137,000 miles per hour, 220,000 km/h. Astronomers were already captivated by its enormous scale, with initial estimates suggesting a nucleus potentially more than 10 kilometers wide, making it much larger than its predecessors, Oumuamua and 2I Borisov. The narrative changed dramatically in early September 2025. September 7th, amateur astrophotographers Michael Yeager and Gerald Riemann taking advantage of the dark skies of Namibia during a total lunar eclipse, an event that naturally reduces lunar glare and improves deep sky visibility. Deep images of the comet were captured. These images revealed the impossible. The coma, the cloud of gas and dust surrounding the nucleus, was now bright, intense, and unmistakable green. The reaction of the astronomical community was shock and urgency. While comets often display a greenish tint, usually due to the presence of diatomic carbon C2, the intensity and moment, the green color of 3I Atlas created an immediate puzzle. Previous spectroscopic studies conducted in August had suggested that the comet was actually exhausted carbon chain, implying that it shouldn't have enough C2 to produce such an intense color. The transformation from a dusty reddish coma to a bright, gaseous green one indicated a quick change in the activity and composition of the comet as it approached the Sun. The bright green light served as a sudden and undeniable indicator that 3I Atlas was much larger, chemically active and volatile than the comets in the solar system. This was not the expected behavior of a frozen, dusty, well-baked rock. It was the erratic outburst of an alien world. Deep green was quickly associated with potential sharp increase in cyanide, CN production, a compound closely related to the molecule C2, often responsible for the green glow as indicated by observations by the European Southern Observatory's Very Large Telescope. The emerald shroud was, in fact, a spectroscopic alarm bell, indicating that the ancient ices deep within its core were sublimating with unprecedented and unstable fury, forcing astronomers to immediately redouble their efforts to decode the message written in its alien chemical fire. The large size of 3I ATLAS, along with its highly anomalous CO2-rich composition revealed by the James Webb Space Telescope, and now this striking, brilliant green display has cemented its status not just as a rare visitor, but as urgent cosmic chemical laboratory, a messenger from the dawn of the galaxy whose true nature demanded immediate and thorough investigation. The bright, almost alarming green hue of 3I ATLAS is the direct result of a fundamental cosmic chemical reaction, one that has puzzled astronomers for nearly a century. But in this specific interstellar visitor, it is showing unusual high-intensity signature that screams alien chemistry. The key green glow in Comet, the gaseous cloud around the nucleus of almost all comets, is caused primarily by a highly reactive molecule known as diatomic carbon, thedicarbonato, C2. The origin. C2 doesn't reside directly on the comet's icy surface. Instead, it's a breakdown product. As the comet approaches the Sun, the heat causes larger organic molecules, carbon-rich ices, such as acetylene or more complex hydrocarbons, to sublimate or convert directly into gas. The formation. Once these larger molecules are in the gaseous coma, the Sun's powerful energy, ultraviolet, UV, radiation, the same substance that causes sunburn, acts like a chemical knife, photodissociating them. This process removes the lighter atoms, leaving behind the simpler, but highly energetic, two-carbon chain molecule, C2, the shining. The C2 molecule then absorbs more energy from the Sun and immediately emits that energy in the visible light spectrum. This emission is dominated by a specific band of light known as swan bands, which our eyes perceive as bright green. This process perfectly explains why the color green is ephemeral and only visible in the coma, not in the tail.C2 molecules once formed, are quickly destroyed again by the same sunlight that created them, and normally last only about 2 days before breaking down into individual carbon atoms. This destruction occurs before the molecules can be pushed far enough by the solar wind to form a green tail. While the mechanism of C2 fluorescence is well established, 3I ATLAS exhibits several unprecedented chemical characteristics that elevate their green glow from a standard phenomenon to a great cosmic anomaly. Early spectroscopic observations by 3I ATLAS indicated that compared to typical comets in the solar system, it was among the comets with the greatest carbon chain deficit known. This means that based on the initial data, you should have significantly less of the parent molecules that decay to form C2. Logically, a comet poor in these carbon precursors should have a faint, almost imperceptible green haze. However, the images show intense and brilliant emerald shroud. This paradox suggests one of two radical possibilities: a hidden deposit. The structure of this interstellar core is unique and may have a thin, highly volatile outer layer that is now rapidly shedding from an extremely concentrated pocket of parent organic compounds that were previously protected. An unknown precursor. The green glow is being amplified or caused by a different molecule, not identified, formed in an alien star system, one that fluoresces green with even greater efficiency than C2. Complementary spectroscopic observations have also detected significant amounts of cyanogen, CN, a single carbon, single nitrogen molecule, which is chemically related to C2. CN is also a common cometary component, sometimes contributing a slight blue-green tint, but its detection here is coupled with a sharp, and very unstable increase in production. Harvard astronomers and others have argued that the dramatic change in color of 3I ATLAS from red to green may be directly associated with this sharp and pronounced increase in cyanide production. This suggests a deep, volatile internal process in which the comet's nucleus is violently shedding ice, ash hydrogen cyanide, HCene, a chemical fingerprint of ancient, potentially life-forming organic materials. The presence of this toxic substance, along with the mystery of C2's intensity, transforms the beautiful green glow into a spectroscopic warning sign. What increases the mystery is the discovery of the James Webb Space Telescope, JWST, that the coma is heavy dominated by carbon dioxide, CO2. ATLAS has one of the highest CO2 to water ratios ever recorded on a comet, often 6 standard deviations above normal. CO2 is a greenhouse gas, not a source of visible green light, but its overwhelming presence suggests that the interstellar core is structured with an enormous amount of highly volatile ice that sublimates at a lower temperature than water ice. This hyperactive release of CO2 provides violent engine, which is tearing apart the surface, exposing deeper layers and rapidly generating massive amounts of C2 and CN responsible for the comet's vivid and eerie green fire. This is a chemical fingerprint that we have never seen before on a comet in the solar system. A violent, bright green, CO2-fueled anomaly from beyond the stars. The question of what drives the excessive but paradoxical, the release of diatomic carbon, C2, the molecule responsible for the intense green glow, gets to the heart of what makes ATLAS an extraterrestrial enigma. The high activity of C2, despite observation suggesting it should be chemically poor in C2 precursors, points to a volatile and unstable internal structure and a composition completely alien to our cosmic environment. The most convincing explanation for the comet's intense activity and the sudden appearance of the green glow, C2, is its anomalous abundance of frozen carbon dioxide, CO2, lead the highest proportion ever recorded observations of the James Webb Space Telescope, JWST, and the mission revealed that the coma of 3I ATLAS is strongly dominated by CO2 gas. The measured mixing ratio of CO2 and water, H2O, is approximately 8:1, a figure that is not only among the highest ever recorded for a comet, but is statistically 6 standard deviations above the norm for comets in the solar system. The volatility factor. CO2 ice sublimates, turns directly into gas, at a much lower temperature, around 78.5 degrees Celsius, than water ice, 0 degrees Celsius. This means that even when 3I ATLAS was still far away, at distances where water ice remained deeply frozen, its vast reserves of CO2 were already violently sublimating. The internal pressure cooker. This massive and early release of CO2 creates immense internal pressure. This pressure acts as a cosmic jackhammer, cracking the comet's outer layer and extracting material from the inner layers. This violent and uneven outgassing is believed to be the energy source driving the comet's activity. Excessive C2 emission is probably a side effect of the CO2 pressure wave, working in 2 critical ways: exposing primitive ice. Comets often have layers like an onion. The outer layers, slightly heated and baked by previous encounters with distant stars, can be rich in dust and poor in volatiles. The explosive CO2 gas that sublimates from the inside it creates powerful jets that destroy this crust, exposing deeper areas, pristine pockets of highly volatile organic ices. These newly exposed organic compounds are the direct precursors of C2 and CN, cyanide. The green glow is simply a result of this. Fresh and concentrated material being exposed to the sun's ultraviolet radiation for the first time in billions of years. Thermal insensitivity. Another theory suggests that the structure of the interstellar core Perhaps due to its ancient formation or extreme radiation bombardment in its home system, is harder to heat than a typical comet. This inhibition of heat penetration means that CO2, the most volatile ice, sublimates first and aggressively, while the vast reserves of H2O ice remain trapped in the deeper layers. This CO2-driven activity creates the perfect, concentrated environment for C2 formation near the nucleus, resulting in the intense, visible green glow. The enigma deepens because, despite this proposed mechanism, early quantitative spectral analyses suggested that 3I ATLAS was exhausted carbon chain. This brings us to the more radical theories about excessive green. If the proportion of C2 is really low, then the only way to explain the bright green color is if the C2 molecules in this interstellar comet are hyper-efficient in fluorescence due to its unique training conditions, extraterrestrial radiation hardening. The comet may have been exposed to extremely high levels of ultraviolet radiation in their original star system. This radiation hardening could have created molecular structures in the parent organic compounds that release C2 in a much more excited energy state than comets in the solar system, causing the green light 2 orders of magnitude brighter for the same number of molecules. Second, more exotic discovery adds to the instability. The detection of nickel, Ni, in the coma, but not in its typical cosmic companion, iron, Fe, volatile metal compounds. This strange finding suggests that nickel may be bound to a highly volatile molecule, such as nickel tetracarbonyl NiCO4. This compound decomposes easily in sunlight to release gaseous nickel and, crucially, carbon monoxide, CO. Feeding reaction, C2. This nickel-driven CO release could rapidly react with other volatile components to boost the production of C2 precursors, providing a highly energetic secondary reactor. Extraterrestrial chemical pathway due to the intense green emission. In essence, excess C2 is a manifestation of an unstable, volatile and alien interior. The bright green light is the visible consequence of a CO2 pressure wave. It cracks open an ancient shell and exposes exotic, highly concentrated organic ices to our Sun for the first time in galactic history. It's a cosmic eruption, and green is its fiery and unstable signature. The most surprising aspect of 3I ATLAS, it's not its speed, nor its size, nor even its green glow, but the details. Chemical Planet bears a spectroscopic imprint forged in a completely different star system billions of years ago. When astronomers compare this alien composition with the thousands of comets born in our solar system's Oort cloud or Kuiper belt, Atlas's interstellar origin becomes unmistakably evident through a series of striking anomalies. The most significant difference between 3I ATLAS and its solar system counterparts lies in the composition of its volatile ices, specifically the ratio of carbon dioxide, CO2, to water, H2O. The comets of the solar system are fundamentally dominated by water. When they get close enough to the Sun, they release enormous amounts of water vapor, H2O, making water the main component of their comas. CO2 is present, but usually in a mixing ratio of less than 1:10 to water. 3I ATLAS breaks this rule. Data from the James Webb Space Telescope, JWST, and the Ball, the mission shows that 3I ATLAS has a CO2 to water ratio of approximately to 1A statistical outlier. This ratio is one of the highest ever measured in any comet and is astonishing. 1 sigma anomaly compared to the general population of comets we know. Statistically, ATLAS is not just unusual. It is a natural phenomenon by solar system standards. The implication of training. This extremely CO2-rich composition directly points to its extraterrestrial origins. It suggests that ATLAS formed far from its parent star, beyond CO2 ice line, in a region where carbon dioxide ice was immensely abundant, perhaps due to high radiation levels or specific enrichment of its protoplanetary disk. Its home star system exhibited a chemical bias that ours did not. A later and equally profound discovery made by the Very Large Telescope, VLT, in Chile, Atlas's extraterrestrial chemistry stands out even more. The detection of atomic nickel vapor in the comet's coma, but notably without the corresponding detection of iron, the terrestrial standard. In space, nickel and iron are almost always found together, as they are heavy elements that condense. When comets release gases, both elements often sublimate from dust grains. The extraterrestrial enigma. The detection of nickel alone strongly suggests that the metal it comes from standard refractory, rocky dust grains. Instead, it must be sublimating from a highly volatile compound, probably nickel tetracarbonyl, NiCO4. This is a chemical compound so volatile that it breaks down easily and is rarely seen in natural space environments. But it is common in industrial chemistry and certain highly specific formation processes involving abundant carbon monoxide, CO. The unanswered question: the combination of pure nickel and extreme CO2 suggests a unique and potentially violent chemical history, forcing astronomers to confront scenarios that mix ultra-ancient origins with volatile, highly processed metal-organic chemistry. In short, 3I ATLAS is a time capsule infused with carbon dioxide and nickel. This directly challenges our comfortable, water-based assumptions about where and when the building blocks of planetary systems form. Their chemical composition is a powerful reminder that the galaxy is far more diverse and chemically complex than the solar environment we call home. The true revelation carried out by 3I ATLAS in its age, challenging a cornerstone of modern astrophysics, the timeline of when and where the chemical ingredients. For planets and life, it may have emerged for the first time in the Milky Way. The comet's trajectory and chemical signature suggest it is a relic of the Wurzpor in metals, an ancient time long before the birth of our Sun, which forces us to fundamentally review our cosmic history. The first clue about the extreme age of Atlas and its extraterrestrial origin comes from its hyperbolic speed excess, or BFI, the speed it maintains even after escaping the Sun's gravitational influence. Extreme speed. Atlas is traveling through the solar system at a speed of approximately 58 km/s relative to the Sun, significantly faster than its predecessors, Oumuamua 26 km/s and 2I Borisov 32 km/s. This extreme speed reflects its long and turbulent journey through the galaxy. The correlation of age. Researchers link the speed and trajectory of an object to its likely origin within the Milky Way. Objects in the galaxy-thick disk, an older, puffier layer of the galaxy, tend to have higher velocities than the thin disk where the Sun resides. By tracking Atlas's probable galactic orbit, scientists estimate its age to be in the range of from 3 to 11 billion years. The time traveler. Our own solar system is approximately 0.6 billion years. This means that there is a high probability. It is estimated that there is more than a 2/3 chance that 3I ATLAS is significantly older than the Sun, preserving pristine material from an era we can only study by observing extremely distant and faint galaxies. The significance of ATLAS being a thick disk object is directly related to the concept of metallicity in astrophysics. In astronomy, the term metals covers all elements heavier than hydrogen and helium. These heavier elements, such as carbon, oxygen, iron, and nickel, are not formed during the Big Bang. They are synthesized inside stars through nucleosynthesis, and then they were dispersed in space by powerful supernova explosions and stellar winds. Galactic enrichment. The galaxy began as metal poor, composed almost entirely of H and He, and has become progressively metal-rich over billions of years as successive generations of stars lived and died, enriching the interstellar medium with heavier elements. Origin of Atlas. If Atlas formed 7 to 11 billion years ago in the thick disk, its original star system would have been born from a region of space that was significantly less rich in metals than the gas cloud that gave rise to our Sun. This metal-poor origin presents a significant contradiction with the observed chemistry of the comet formation of challenging planets. Traditional models suggested that the formation of complex, carbon-rich ices such as CO2 and C2 parent molecules took a relatively long time, metal-rich environment, one that had enough heavy elements to build dense protoplanetary disks. The Atlas evidence, however, Atlas, a probable relic of this ancient metal-poor era, is hyper-rich in CO2 and exhibits intense C2 and Cn emissions. This suggests that the early metal-poor universe was much more efficient at creating organic ices and complex, volatile planetesimals than predicted by theory. The implication is profound. Massive, chemically complex, water-bearing worlds may have been forming billions of years ago in the history of the universe than we previously believed. Atlas is direct evidence that the basic chemical components of planetary systems and even life were present and firmly embedded in comet-like bodies when the galaxy was still young and chemically primitive. It is a fossil from the dawn of the galaxy, forcing us to rewrite the chronology of cosmic chemistry. The convincing conclusion drawn from the extreme speed and peculiar chemistry of 3I ATLAS, but this interstellar visitor is a geological sample of a cosmic environment of star formation radically different from the one that gave rise to our Sun. An ancient star nursery forged in that was poor in metals from the history of the Milky Way. To understand the origin of Atlas, astronomers use galactic archaeology, which uses the properties of stars and other objects to map the history and structure of the galaxy. Our Milky Way is structurally divided into two main components. The thin disk, the home of the Sun. This is the plane of the galaxy with its spiral arms, rich in gas, dust, and population stars. Younger stars that are relatively rich in metals, chemically abundant in elements heavier than hydrogen and helium. Our Sun and all of its planets and comets formed here approximately 4.6 billion years ago. The thick disk, origin of Atlas. This is a larger, bulging layer that extends above and below the thin disk. It is dominated by older material, population 2 stars that are significantly poor in metals, having formed early in the history of the galaxy before many supernovae had enriched the interstellar gas. The extreme hyperbolic velocity of 3I ATLAS, v58 km/s, and its steep and very inclined path in relation to the plan of the solar system. They are the physical evidence that links it to this ancient population. Rocking motion. The objects in the thick disk do not orbit in an orderly manner. They oscillate vertically relative to the galactic plane. The Atlas trajectory shows this characteristic vertical motion, which rules out its origin in the thin disk of another typical spiral galaxy. Extreme age. The stars in the thick disk can be 7 to 10 billion years by modeling the comet's path around the galactic center. Astronomers conclude that Atlas likely formed in this ancient environment, making it a fossil that predates our Sun by several billion years. The most profound scientific implication of a thick, metal-poor disk origin is that it challenges our understanding of star and planet formation in the early universe. For decades, the prevailing theory was that efficient planetesimal formation, the process of turning dust and gas into kilometer-sized, rocky and icy bodies like comets, required a threshold amount of frail's heavy elements, cooling and condensation. Metals are crucial because they form dust grains, silicates, iron compounds. These dust grains act as cooling agents, For dense gas clouds, this allows the gas to fragment and collapse under gravity to form stars and, subsequently, protoplanetary disks. Without enough metal, the gas remains too hot to condense efficiently. The flaw of the model. However, ATLAS suggests otherwise. This comet formed in a chemically primitive region, but its massive size, probably the largest interstellar object found so far, and its incredible chemical complexity, high fractions of CO2 and C2, demonstrate that planetesimals were forming in a robust and efficient manner in environments that we thought were chemically sterile. The existence of a huge, hyperactive, metal-poor comet like ATLAS implies a revised model for the ancient stellar nursery, the carbon cooling channel. In a metal-poor environment, trace amounts of carbon and oxygen present, elements essential for CO2 and C2, must have played a much more dominant role in cooling the star-forming gas than previously thought. The dust that formed may have been dominated by carbonaceous grains, which are excellent capacitors. Early water and organic matter confirms that the ice blocks needed for habitable worlds. Water, carbon dioxide and complex organic compounds were not an invention of the relatively metal-rich Sun. They were common in the ancient universe. That is, the precursors of life were distributed globally through the Milky Way from its earliest and most formative stages. In essence, 3I ATLAS is a unique piece of frozen evidence that the galactic environment 7 billion years ago, far from being a chemically simple wasteland, was active, efficient and fertile nursery capable of spitting out massive and complex icy worlds and injecting them into the intergalactic void long before Earth had a name. The mere age of 3I ATLAS, estimated to be 11 billion years old, means that this comet has spent most of its existence suspended in a billion-year deep freeze, traveling through the near vacuum of interstellar space. This deep, prolonged cosmic journey is precisely what allowed it to act as pristine capsule, locked in time, delivering a sample of primordial alien chemistry to our doorstep. The preservation of ATLAS's strange chemical ratios, the predominance of CO2, exotic nickel, and ancient organic compounds is a testament to the efficient cold storage provided by the interstellar medium, ISM. Temperature lock. In the space between star systems, temperatures typically hover around 3 Kelvin, 270 degrees Celsius or 454 degrees C. This is well below the sublimation point of even the most volatile ices, such as carbon monoxide, CO, methane, CH4, and the abundant carbon dioxide, CO2. Preservation of amorphous ice. In such extreme cold conditions, water ice does not form the orderly crystalline structure we see on Earth. Instead, it forms amorphous ice, a highly disordered, porous, glass-like state. This porous structure is scientifically crucial because it can trap massive amounts of highly volatile gases, precursors of CO2, CO, CN, within their matrix, fixing them in place. This mechanism explains the availability from the huge reservoir of CO2 that now fuels ATLAS's intense activity near the Sun. For billions of years, the amorphous ice acted as a high-security vault, preventing any slow thermal decay or gas leakage. Furthermore, the comet's nucleus itself provided crucial protection for its inner layers, ensuring that only the most superficial material was disturbed during its travels. Car insulation. The comet's nucleus is essentially a large, dirty, non-uniform snowball. It likely has an outer layer of dark, refractory, rocky material, a remnant of its formation that was either deposited early on or formed by the disintegration of complex organic compounds due to radiation exposure. This dark crust acts as an excellent thermal blanket, preventing minimal heat from encounters with distant stars or internal heat release from radioactive decay from penetrating deep into the core. Gamma-ray shadow. Atlas's enormous size, estimated at up to 5 kilometers in diameter, is a critical factor. As it travels through interstellar space, the comet is constantly bombarded by key galactic cosmic rays, GCR, high-energy particles moving at a speed close to that of light. These GCRs have enough energy to penetrate a few tens of meters into the surface, causing radiolysis, breaking chemical bonds, and creating a thin, radiation-damaged layer known as the baked shell. However, the core's large size means that the ancient primordial material at its heart, containing the strange compositions of CO2 and nickel, remains absolutely pristine and chemically intact, protected by billions of tons of ice and rock above it. The journey through the ISM was not entirely without consequences, and the small chemical changes the phenomena occurring on the surface are key to explaining the comet's current activity. Chemical synthesis. The constant, low-level bombardment of gamma rays and ultraviolet radiation in the interstellar medium could have created new compounds near the surface from the H2O and CO2 ices. Astrochemists theorize that some of the detected CO2 could have formed on the surface over billions of years because of this radiation processing, resulting in the incredibly high CO2 content now being released. The trigger. When Atlas finally passed the heliopause and entered our solar system, the sun's heat began to penetrate the baked layer. This heat first reached the highly volatile CO2 processed by radiation and the gases trapped within the amorphous ice. The massive and immediate outgassing observed is not just sublimation. It is the sudden volatile release of billions of years of stored energy and trapped gas, violently opening the outer layer to reveal the pristine, metal-poor core beneath. The billion-year deep freeze period wasn't just a storage period. It was a period of perfect preservation which has now culminated in a violent emerald green burst. A spectacular moment in time when 11 billion years of chemical history are laid bare for our telescopes to decode. The moment 3I ATLAS was sighted, its trajectory immediately pointed to its extraterrestrial origins, initiating a cosmic game of gravitational pinball. This confirms that it is simply a transient visitor. However, the exact nature of its trajectory has become a major source of controversy, with anomalies challenging both our understanding of cometary physics and galactic statistics. The first and most undeniable proof of the interstellar nature of Atlas is its hyperbolic orbit extreme eccentricity. In orbital mechanics, a value known as eccentricity E dictates an object's trajectory. Orbits that form loops, such as those of the planets and comets in the solar system, have an eccentricity less than 1e1. Objects that escape the system have an eccentricity greater than 1e1, which means that unidirectional and unlimited hyperbolic trajectory. Massive outlier. While the previous interstellar objects, Oumuamua E1.2 and 2I Borisov E3.6, were already hyperbolic, 3I ATLASIT has an extreme eccentricity of approximately E6.14. This value is so high that its path through the solar system is almost straight, confirming that it is moving too fast to be captured by the sun's gravity. Hyperbolic speeding. This high eccentricity is reflected in its entry velocity with respect to the sun, known as hyperbolic speed excess, V, which is a staggering 58 km/s. This speed is a gravitational remnant of its eons of travel, confirming that no amount of solar gravitational braking will prevent it from leaving our system for good. The certainty of its interstellar origin quickly gave way to a controversy over his specific trajectory once inside the solar system. How does the comet's trajectory appear? Statistically anomalous in two key ways. Interstellar objects, having been randomly ejected from star systems throughout the galaxy, are generally expected to approach our solar system from random directions, typically at steep and unpredictable angles to the plane in which the planets orbit, the ecliptic plane, unnaturally flat. Surprisingly, Atlas's orbital plane is tilted only about 5 degrees with respect to the ecliptic, meaning it slides almost perfectly along the flat disk where the planets reside, albeit in a retrograde direction opposite to the movement of the planets. The statistical failure. Astronomers calculate that the probability of a randomly arriving interstellar object having such a close alignment with the ecliptic plane is extremely low. Some estimates put the random probability at only 1 in 500 or less. This statistical anomaly has led some researchers, notably Harvard professor Avi Loeb, to suggest, as a pedagogical exercise, that such an alignment could be intentional, the optimized route for an artificial technological probe designed to study multiple planetary bodies. In cometary physics, outgassing acts like a small rocket booster, causing a slight, measurable deviation from the trajectory predicted by gravity alone. This is called non-gravitational acceleration. The mass anomaly, despite the James Webb Space Telescope, by detecting a colossal mass loss rate of approximately 150 kilodalits of CO2 vapor, a huge amount of material that should produce a significant push, ATLAS has demonstrated almost no measurable non-gravitational acceleration in the tracking data. The massive solution. For ATLAS to be able to disseminate so much material without significantly deviating from its course, it must be enormously massive. New calculations suggest that the nucleus is much heavier than originally thought, with a mass greater than 33 billion tons and a minimum diameter of 5 kilometers. This implicit mass makes ATLAS reach up to 3 to 5 orders of magnitude more massive than previous interstellar visitors, Oumuamua and Borisov, which in itself is a statistical anomaly in the galactic population of planetesimals. The comet's trajectory is therefore a double mystery. On the one hand, it is definitely interstellar, confirming that our galactic direction is a well-trodden crossroads. On the other hand, its unnaturally aligned, yet minimally perturbed trajectory has sparked intense debate. Is this an extremely rare object with an unnatural mass following a natural orbit with a probability of 1 in a million? Or is its trajectory and stable nature a sign of something beyond the natural physics of comets? The upcoming flybys of Mars and Jupiter are now seen as crucial opportunities to gather data that could finally resolve the truth behind this gravitational enigma. The intense degassing observed from 3I ATLAS is a fundamental astrophysical contradiction, a phenomenon that should not be occurring with such fervor at the vast distances where the comet was first detected. Outgassing paradox provides the clearest chemical evidence of the comet's alien and volatile nature and highlights the enormous pressure cooker at its heart. For comets formed in our solar system, activity is a function of solar proximity. The water ice line. The reference point for cometary activity is the water ice line, typically about 2.5 to 3.0 astronomical units, AU, from the Sun, roughly 2.5 to 3 times the distance from Earth. Beyond this point, solar radiation is usually too weak to sublimate the most abundant volatile water, H2O. The Rape of Atlas. 3I ATLAS shattered this expectation. It was first detected in July 2025 at a heliocentric distance of 4.5 AU, approximately 680 million kilometers from the Sun, well outside the traditional H2O activity zone. Even more surprisingly, pre-discovery observations showed that the comet was already bright and active up to 6.4 AU, an area where only the most volatile ices, such as carbon monoxide, CO, are normally active. However, the activity was intense enough to form a distinct, developing coma. This profound difference means that the sublimation driving Atlas's activity must come from a completely different volatile source than typical solar system comets. The solution to the paradox lies in the comet, anomalous chemical composition, As revealed by the James Webb and SphereX missions, its extreme abundance of frozen ice carbon dioxide, CO2, low sublimation temperature, CO2 ice sublimates at a much lower temperature, around 78.5 degrees, than water ice, 4 degrees. This crucial difference means that even the weak sunlight at 6 AU, where the Sun appears as a tiny, distant disk, was enough to heat the comet's surface enough to trigger massive CO2 outgassing. Dominant volatile. The CO2 to H2O ratio of 8.1 confirms that Atlas is a fundamentally CO2-rich body. It is an extraterrestrial CO2 iceberg, while comets in the solar system are usually water icebergs. This volatile difference explains why Atlas was activated so far from the Sun, where a water-based comet would remain inert and dark. The outgassing rate is astonishing. Even at distances of about 3.3 AU, the comet was ejecting material at a rate of about 150 kilograms per second, the CO2 output of millions of human beings, while displaying only a minimal or undetectable amount of water vapor, confirming that CO2 was the dominant propellant. Beyond the low sublimation temperature of CO2, the sustained large-scale activity at such distances suggests two hypotheses related to the comet's internal structure. Trapped gas catastrophe. For billions of years in the frigid interstellar background, the comet's amorphous water ice trapped colossal amounts of highly volatile gases, including CO2, CN precursors, and possibly even CO2 within its porous matrix. The minimal heating from our Sun could have triggered crystallization of amorphous icy near the surface. This phase change acts as a pressure release valve, violently expelling the enormous reserves of trapped gas, causing intense and early degassing. Internal radiogenic heating. The comet may contain a concentration of short-lived radioactive isotopes embedded in their rocky core. While negligible for large planets, the decay of these isotopes may provide a small but crucial source of internal heating within an insulating cometary nucleus, heating the most volatile ices, CO2 and CO, from the inside out and contributing to the widespread activity observed far from the Sun. Heat outgassing paradoxite is therefore a direct window into the comet's alien formation. The comet's brilliant activity, far beyond the water ice line, is not a mistake of solar physics, but a profound demonstration of its unique, primordial chemistry, a volatile, CO2-rich heart that finally erupts after billions of years of silent galactic journey. The most visually dramatic evidence of 3I Atlas internal instability is its behavior in the photometric light curve. The sudden and unpredictable sudden increases in brightness and flares, these are not smooth, predictable increases in brightness. They are erratic outbursts, which reveal the chaos of an alien core desperately trying to contain enormous internal pressure. Comets typically follow a predictable trend of increasing brightness as they approach the Sun, with their brightness increasing inversely as the square of their distance from our star. Atlas has constantly challenged this cosmic label, violent flashes. Observers following the comet have recorded multiple short-lived episodes in which its overall brightness sudden spikes above the established trend line. These explosions are known as flares or bursts, and while common in some comets in the solar system, their frequency and magnitude in Atlas are very unusual, especially given its immense distance at the time of initial activity, pre-discovery activity up to 4 AU, most pronounced trend. Furthermore, the overall rate at which Atlas has increased in brightness is significantly steeper than that of the previous interstellar comet, Borisov. This suggests that as the comet approaches, the rate of sublimation is not a gradual, smooth heating, but a runaway, rapidly accelerating process driven by immense internal forces. The main cause of these sudden increases in brightness is the fragmentation of the comet's outer dust blanket, the protective crust that prevents ice from vaporizing prematurely. As established by JWST and SphereX, the Atlas core is enormously rich in low sublimation temperature ices, specifically CO2. The heat of the sun penetrates the surface and reaches the CO2 ice, causing it to quickly turn into gas. Pressure buildup. This gas vapor is trapped beneath the insulating layer of rock and dust that forms the outer mantle. Since the gas cannot easily escape, pressure builds up in a localized underground cavity. The pressure is exacerbated by the fact that the comet's force, massive size, it gives it a greater gravity than smaller comets, making it harder for material to be released. Explosive release, flare. When internal pressure exceeds the structural strength of a weak point in the overlying crust, gas erupts violently, destroying a localized area. Jet of dust and gas into space. This sudden release of reflective material causes the comet's apparent brightness to increase immediately, outbreak, before the gas dissipates and the brightness returns to background level. Even Atlas's regular and constant activity indicates instability. Photometric monitoring suggests a core rotation period of approximately 16.16 hours. Light curve analysis shows higher order harmonics, multiple brightness peaks within a single rotation, which strongly suggests concentrated jets and CO2 degassing is non-uniform across the sun-facing surface. Instead, it is likely to concentrate on discrete and very active jets, possibly only 2 or 3, which eject material as they rotate sequentially toward direct sunlight, asymmetric thrust. This type of asymmetric outgassing is the mechanism that causes comets to experience the subtle but measurable non-gravitational acceleration which pushes them out of their orbits, defined purely by gravity. For Atlas, the fact that their measured non-gravitational acceleration is insignificantly small, as discussed in the previous chapter, further supports the theory that its immense mass resists the thrust, essentially turning those powerful jets into the equivalent of a small sneeze. The brightness increases of 3I Atlas are therefore dramatic visual reminders of alien, ancient pressure vessels subjected to solar heat for the first time in eons. The unpredictable flashes are the sound of its CO2-rich inner core rupturing under the pressure of galactic-scale thermal stress. The emerald glow that makes Psi Atlas so visually striking is at the same time the greatest barrier to understanding its true nature. The comet's massive and hyperactive atmosphere, or coma, acts as a shining veil, completely obscuring the solid, icy core of its nucleus, giving rise to one of the most persistent controversies. How big is the alien heart? The challenge of observing the core is a direct result of the extreme activity we have already discussed. Rampant CO2-driven outgassing, scattered light. The green coma is composed of large amounts of gas, C2, CO2, CN, and tiny reflective particles, dust particles, violently ejected by sublimated ices. The light we see, the vast majority of the comet's brightness, does not come from the nucleus itself, but sunlight is scattered by this huge cloud. Dominant signal. The volume of the coma is colossal and extends hundreds of thousands of kilometers into space. Even the world's most powerful telescopes, such as the Hubble Space Telescope, HST, struggle to penetrate this dense, glowing fog to make out the tiny, dark, solid body at its center. The light from the core is simply drowned out by the intense reflection from the surrounding layer of expanding alien material. The blurry dot. Astronomers can only track the comet photocenter, the brightest point of light, which is the center of the coma, not necessarily the actual nucleus. This inability to locate the solid nucleus means that the most fundamental property of the object, its actual size and mass, remains an estimate subject to significant uncertainty. The darkened nucleus has led to a scientific tug-of-war over the comet's dimensions, driven primarily by two competing analytical methods. To constrain the size of the nucleus, astronomers analyzed the surface gloss profile, how quickly the intensity of the light decreases as one moves away from the center of the comet. The upper limit of 2.8 kilometers, by modeling the outflow from the coma and subtracting its expected light contribution, the HST team was able to establish a strong upper limit. The nucleus's radius is estimated to be no larger than 2.8 kilometers, 5.6 kilometers in diameter. This range, which places the nucleus potentially from a few hundred meters to 5.6 kilometers, is consistent with the sizes of other known comets. However, this conventional size estimate directly conflicts with the observation that the comet displays almost no measurable non-gravitational acceleration. The impulse paradox. We know that the comet is breaking away 150 kilograms per second of propellant, CO2 gas. To resist the thrust of the corresponding rocket and remain on its intended gravitational trajectory, the core must possess an enormous amount of inertia, time, the minimum of 5 kilometers. By analyzing the upper limit of the detected non-gravitational acceleration, the researchers have calculated that the core must have a minimum diameter of at least 5 kilometers and a corresponding minimum mass of more than 33 billion tons. This finding suggests that Atlas must be a massive, dense, and physically large object to withstand the pull of its own intense outgassing. The green veil hides a crucial truth. Atlas is a 5.6 kilometers object at the limit of the typical size of a comet, or it is much larger, anomalously dense an object that actively resists our models. Ironically, the intense light of the coma prevents us from appreciating the true magnitude of the interstellar visitor at its closest approach. The Mars flyby is crucial because it offers the only opportunity for spacecraft like the Mars Reconnaissance Orbiter, MRO, use its powerful high-rise camera to image the core with higher resolution than ground-based telescopes, potentially cutting through the veil to reveal the true size of the solid core. The risk of fragmentation is rooted in the unique and unstable conditions that exist deep within the interstellar core. The central issue is the hypervolatile composition. Dominated by CO2 as discussed, the sun's heat is causing massive sublimation of CO2, creating huge volumes of gas trapped beneath a blanket of surface dust, mechanical failure. The bursts of brightness are visual evidence of the collapse of the core's crust under this internal pressure. Each flare is a mini explosion. As the comet approaches the sun, the rate of CO2 sublimation increases exponentially, imposing ever-increasing pressure. Mechanical deformation in the remaining nuclear structure. If a major flaw or weak point, perhaps a crack from its original accretion or damage from interstellar cosmic rays, gives way, the entire body could suffer catastrophic failure. Intense, asymmetric gas jets also pose a rotational hazard. Concentrated jets of gas act like propellants for off-center rockets. Over time, these jets can increase the comet's speed, rotation speed, which causes it to spin faster. As the spin rate increases, the core is subjected to greater centrifugal force, which attempts to separate low-density material and loose aggregates. Tidal forces. Although solar tidal forces are negligible at its current distance, the combined effect of rapid spin and internal pressure brings the core dangerously close to its tensile strength limit. Small increase in jet intensity could push the already fragile structure beyond its breaking point, causing fragments to be thrown off the equator. In an event that immediately raised concerns about planetary defense, early tracking data revealed a second object behind 3I Atlas near Mars. First interstellar division. This observation, if definitively confirmed as a fragment of Atlas, would mark the first suspected interstellar fragmentation event observed in our solar system. The detection of a secondary fragment of kilometer-scale debris would demonstrate that the core instability is not merely theoretical, but is actively developing despite the comet's enormous size. Sudden change of direction. This fragmentation may be correlated with a recent and unexplained phenomenon. Sudden change in the comet's rotation, speed documented in observational records. Such an abrupt rotation change is a classic sign of a large piece of dough being ejected from the nucleus, dramatically altering the comet's moment of inertia. The history of comets in our own solar system offers grim precedents for what happens when large, unstable bodies encounter the Sun's gravity. The most famous example is Shoemaker-Levy Comet 9 in 1994. Although it was tidally disrupted by Jupiter's gravity, its fate is a chilling reminder of how a single object can become a chain of deadly projectiles. The fragmentation of Atlas would not be contained by Jupiter's gravity, instead creating a broad debris field that would traverse the inner solar system. Throughout history, large, active comets have disintegrated at an astonishing rate. White Comet. This short-period comet split into two parts in 1846, and by 1852 they had separated by more than 2.4 million kilometers before completely dissolving. Its debris stream subsequently produced a spectacular but troubling meteor storm. Kreutz Sun Chasers. This entire family of comets originated from the fragmentation of a single, exceptionally large progenitor comet estimated at over 100 kilometers across, approximately 1,700 years ago. Its cascading fragments continue to threaten the inner solar system and are a clear example of how a rupture event can generate a continuous flow of hazards for millennia. The fragmentation of 3I Atlas, a body potentially older and more chemically volatile than any other in our Oort cloud, would not only be a momentous scientific event, but also a clear demonstration of the inherent high-speed danger that every interstellar visitor contains. The Emerald Veil isn't just a beautiful glow, it's volatile vaporizing from a relic on the brink of catastrophic structural failure. The discovery of water vapor emanating from 3I Atlas, it's more than just confirmation that it's a comet. It's the moment astronomers received ice cube between 7 and 11 billion years old, a pristine, frozen sample of water from a completely different star system in the ancient and metal-poor galaxy. This water is not only ancient, its presence in this context has profound implications for the cosmic origin of water on all planets. Initially, the large volume of carbon dioxide, CO2 degassing, led some to believe that water, H2O, might be severely depleted in Atlas, or at least heavily suppressed. UV detection, however, the observations of the Observatorio Neil Gehrels Swift, using its ultraviolet optical telescope, UVOT, it successfully detected the emission of hydroxyl radicals, OH, which is the product of the direct decomposition of water vapor in sunlight. This confirmed that 3I Atlas is actively releasing H2O remote activity. Crucially, this water activity was confirmed at a heliocentric distance of 3.51 AU, very far from the orbit of Mars. For a typical comet, the sublimation of water ice at this distance is highly inefficient. For Atlas to produce an estimate 40 kilograms per second of water vapor in this range implies a surprisingly large and extended active surface. Calculations suggest more than 20% of the comet's surface is actively releasing H2O, a value 4 times greater than the average of 3–5% of comets in the solar system. The high activity rate, even at a distance, is a demonstration of the enormous reserves of H2O deep within the core, which are eventually released after eons of preservation. The importance of this detected water is inextricably linked to the comet's extreme age and its metal-poor origin, the question of age. Since models suggest that 3I Atlas originated in the ancient Milky Way, thick disk forming up to 7 billion years ago, the water ice within its core is essentially primordial. It is water that formed in the cloud of dust and gas surrounding its distant parent star, possibly 2 to 3 billion years before the Sun existed, challenging the origin of Earth's water. The persistent debate is whether Earth's vast oceans were brought in by comets and asteroids, or whether water formed locally in the young, hot solar nebula. If interstellar water in Atlas is found to have a similar composition, deuterium-hydrogen ratio, a chemical signature or fingerprint of its formation temperature, to Earth's oceans, would strengthen the argument that a significant fraction of the water on all planets originated in the vast, cold interstellar clouds that existed before star was born. Atlas provides us with a direct, chronological sample of that initial supply of galactic water. The discovery of abundant water ice, albeit temporarily overshadowed by excess CO2, in an object that originated in a chemically primitive, metal-poor environment is a powerful cosmological statement. Frozen abundance. It confirms the hypothesis that the cosmic waterline was omnipresent throughout the early galaxy. Despite the low metal content, the formation processes, water-rich planetesimals were highly efficient. Implications for exoplanets. If H2O was readily available to systems billions of years ago in metal-poor regions, it greatly increases the expected prevalence of its rich exoplanets with oceans and icy moons throughout the history and structure of the Milky Way. Water, the key ingredient for life as we know it, is not a rare late product of cosmic evolution, but a universal and ancient constant. In essence, the detection of water vapor from 3I Atlas is not just an astronomical footnote, it is the physical confirmation of a long-standing cosmological hypothesis. The galaxy has been a water-rich environment since its dawn, turning this comet into a literal time capsule of the universe's most precious resource, the most tempting secret hidden behind the bright green veil of 3I Atlas, the confirmation of its rich payload of organic molecules, the fundamental chemical units of life itself. This spectroscopic evidence transforms the comet from a simple icy rock into a spaceship carrying the interstellar seeds of life, deeply reinforcing the old and controversial hypothesis of panspermia. While the dominant volatile in the Atlas coma is CO2, infrared and ultraviolet spectroscopy has confirmed the presence of a suite of complex organic species that are crucial components of prebiotic chemistry: hydrogen cyanide, HCN. Detection of the cyanogen radical, CN, which contributes to the green-blue glow, occurs from the decomposition of parent molecules. Mainly, hydrogen cyanide, HCN. HCN is one of the most robust and important prebiotic molecules. It is theorized that in Earth's early oceans, HCN was a key starting material for the formation of amino acids and nuclear bases, the molecular bases of DNA and RNA carbon-rich ice. The violent sublimation of CO2 is tearing away layers of ice that are intricately mixed with complex carbon-rich compounds, the precursors of C2, which gives the comet its intense green color. These molecules, which possibly include alcohols, aldehydes, and complex hydrocarbons, represent the pure essence of galactic chemistry. The overall chemical profile of Atlas, despite its 8,1-CO2-H2O anomaly, is remarkably consistent with the basic toolset of organic chemistry needed to initiate life. The discovery of these primordial, complex organic compounds within a body that has spent billions of years traversing interstellar space lends overwhelming weight to the concept of panspermia, the hypothesis that the building blocks of life, or even latent life itself, are distributed throughout the cosmos via celestial bodies. The least controversial form of this idea is pseudo-panspermia, suggesting that comets and asteroids act as delivery vehicles for prebiotic ingredients necessary for life to emerge on a habitable world. The interstellar reservoir. ATLAS demonstrates that the interstellar medium, the vast empty space between stars, is not chemically sterile. It's a massive cold reservoir where complex organic synthesis occurs, and these ancient metal-poor comets are the frozen cargo ships that transport this material across the galaxy. History of the origin of the Earth. This supports the idea that billions of years ago, a shower of comets and meteorites, including, potentially, interstellar visitors, provided the initial supply of water and organic molecules that laid the foundation for life on Earth. The origin of life may not have been a single, spontaneous event on our planet, but rather a final assembly process fueled by universal ingredients in the galaxy. While Atlas's 58 km velocity makes it too fast to be a plausible vehicle for launching intact, living microbes, the impact velocity on a planet would vaporize most of the material. The presence of robust organic precursors is highly significant, densely packed systems. Research suggests that in peas in a pod, in exoplanetary systems, where planets orbit very close to each other, the trajectory of an interstellar comet could be bounced gravitationally between planets. This repeated interaction would act as a cosmic braking system, slowing the comet down to the critical speed of less than 15 kilometers necessary for organic molecules to survive atmospheric entry and impact. Universal Starter Kit. ATLAS is physical proof that every young star system in the galaxy has access to the same ancient universal starter kit for life, making the potential for abiogenesis, the process by which life arises from non-living matter, a matter of chance rather than rarity. The ancient glowing green messenger is not merely a scientific curiosity, it's a profound cosmological statement. The seeds of life are ubiquitous and have been since the dawn of the Milky Way. The flyover of 3I ATLAS, the close pass, by Mars on October 3, 2025, represents a cosmic convergence, a rare moment when an interstellar traveler will be seen not from the disadvantage of Earth, but from the vantage point of 30 million kilometers, 18.6 million miles, from the Martian neighborhood. This unique opportunity has prompted a coordinated effort to repurpose the outdated, but invaluable, NASA and ESA mission. Mars orbiters and dedicated astronomical observers who act collectively as the eyes on the comet. The main advantage of observing ATLAS from Mars' orbit is proximity and visibility. Closer view. The comet's closest approach to Mars is almost 10 times closer than its closest approach to Earth, which offers a geometric advantage that translates directly into greater potential resolution. Solar conjunction bypass. Critically, ATLAS reaches its perihelion brightest point in late October. During this period, from Earth, the comet appears very close to the Sun in the sky, solar conjunction, which temporarily makes observation impossible. However, Mars orbiters are strategically positioned to capture data during this time, critical window of maximum activity, when ground-based telescopes are blind. Two of NASA's primary Mars orbiters have been tasked with leveraging their unique instruments to extract critical data about the interstellar visitor. Mars Reconnaissance Orbiter, MRO, designed primarily to explore the Martian surface and transmit data, has the most valuable instrument for studying the physical structure of ATLAS, the high-resolution imaging science experiment HiRISE camera. Cutting the veil. HiRISE is renowned for capturing centimeter-sized features on Mars. While ATLAS is 30 million kilometers away, MRO's observation will be a crucial test for determining the size of hidden core. Chapter 11. Scientific objective: astronomers hope that high-rise images will allow them to confirm core size, the amount of sunlight reflected from the brightest central pixel, when corrected for the distance and albedo of the comet, will provide the definitive restriction over the actual surface of the core. This measurement is key to resolving the controversy over whether ATLAS is 5.6 kilometers wide, Hubble limit, or larger than 5 kilometers, mass anomaly minimum. Detect fragmentation. HiRISE will look for any clear evidence of recent activity. Fragmentation, see Chapter 12, as a distinctive secondary piece of the core or a debris assemblage, which would indicate catastrophic instability. Map jet locations. High resolution can allow imaging of the concentrated dust plumes or jets emanating from the nucleus, helping scientists model the forces driving the comet's spin and chaotic behavior. Expert, the orbiter, whose mission is to study atmospheric escape mechanisms on Mars, is particularly well suited to investigating the interaction between ATLAS's volatile coma and the Martian environment. Atmospheric interaction. MAVEN has a suite of instruments designed to measure solar wind interactions, including spectrometers and plasma detectors. These instruments will observe ionizing radiation. The comet's CO2-rich coma and associated nickel and cyanide gas create a high-density temporary plasma environment. MAVEN will measure how this alien plasma interacts with Mars's weak remnant magnetic field, the ghost shield, which is crucial to understanding the potential atmospheric depletion effects. Chapter 16. Chemical tracing. MAVEN's mass spectrometer could directly sample any minute amount of interstellar gas, such as CO2 or H2O, that managed to penetrate the upper atmosphere of Mars, providing a pristine, uncontaminated sample of the ancient comet's vapor for direct analysis. NASA's efforts are reinforced by the European Space Agency, ESA, whose orbiters, like the Trace Gas Orbiter, TGO, and Mars Express. The astronauts are also instructed to point their cameras and spectrometers toward the interstellar visitor. This unprecedented international coordination underscores the scientific value of this brief. Unique flyby. Mars orbiters transform the study of 3I ATLAS from a distant theoretical exercise to a direct physical investigation, maximizing scientific return before this billion-year-old Voyager disappears into the cosmic void. The closest flyby of 3I ATLAS will occur on Mars, putting the immense and transient coma of the interstellar comet in direct contact with the most peculiar characteristic of the red planet, its weak and fragmented magnetic shield, an invisible protective layer often called ghost shield. This rare encounter will transform Mars' orbit into a cosmic laboratory, allowing orbiters like MAVEN to study the planetary magnetic field under conditions impossible to replicate on Earth. Unlike Earth, which has a powerful global magnetic field generated by its molten core, a dynamo, Mars's global magnetic field disappeared billions of years ago. What remains are strong, localized areas of magnetism. Magnetic fields of the crust, embedded in the planet's southern crust. A patchwork shield. This fragmented shield is highly localized, but strong enough to create protective pockets that deflect the solar wind, the ceaseless stream of charged particles that flows from the Sun. The induced magnetosphere. Mars defends itself mainly by means of induced magnetosphere. When the solar wind hits the Martian atmosphere, it creates an electric current in the ionosphere, the charged upper atmosphere. This current, in turn, generates a weak, temporary magnetic field that envelops the planet, providing a fragile layer of defense, the ghost shield. When 3I ATLAS, when it passes Mars at a distance of 30 million kilometers, its colossal high-speed coma will sweep through the planet's induced magnetosphere, creating the sea of plasma of strange, Volatile rich gas, the comet itself is surrounded by its own powerful magnetic field, which is generated by the interaction of the solar wind with the comet's charged and rapidly sublimating gases, mainly CO2 and H2O ions. The Siding Spring precedent. The effects of such an encounter were witnessed in 2014 when the comet dock lining it passed much closer to Mars, off our 140,000 kilometers. NASA Data Maven, Mars Atmosphere, and Volatile Evolution. The orbiter showed that Siding Spring's magnetic field temporarily fused and completely overwhelmed the induced field of Mars, which plunges the Martian magnetosphere into complete chaos. The planet's magnetic field lines were violently deformed and disconnected, momentarily destroying part of the upper atmosphere. The ATLAS test Maven's instruments, including its magnetometer and suprathermal and thermal ionic composition, static. The instrument will monitor whether ATLAS's enormous, high-speed coma, despite its greater distance, produces a similar deeper disruption. The key difference lies in speed and composition. ATLAS is faster and is releasing CO2 and nickel vapor, extraterrestrial components that could create completely different and potentially more persistent plasma instabilities in Mars's magnetosphere. Maven's primary objective during the flyby is to study the effect of comet plasma on the Martian ionosphere, ionizing radiation. The comet's high CO2 content means its coma is rich in CO2 ions and secondary electrons. As this high-speed charged material passes close to Mars, it will bombard the upper atmosphere, potentially increasing electron density in the ionosphere and creating intense planetary activity. Auroral displays around patches of the crust's magnetic field in the south. Risk of radio blackout. This severe disturbance of the ionosphere could cause days or weeks of radio interference and signal interruptions for all Mars orbiters and surface assets, such as the Curiosity and Perseverantia rovers, temporarily cutting off humanity's digital connection to Mars. The mission, designed to understand how Mars lost its ancient atmosphere, will record the effects of this massive injection of interstellar plasma, a brief and chaotic event that gives scientists a unique opportunity to see Mars' atmosphere under extreme alien pressure. The flyover of 3I ATLAS near Mars presents a unique and disconcerting scenario: the potential atmospheric injection of alien chemistry toward the fragile upper layers of Mars, risking pollution a planet central to the search for life and the future colonization of humanity. This scenario is no longer theoretical, as the volatility of ATLAS guarantees deep interaction. The 3I ATLAS coma is not composed of passive, inert dust. It is a massive, high-velocity cloud dominated by exotic, chemically active species. Carbon dioxide, CO2. ATLAS is a CO2-rich iceberg that releases gas at a rate of about 150 kJ. While CO2 is the main component of Mars' current thin atmosphere, this massive and sudden injection of interstellar CO2 could temporarily alter isotopic equilibrium and atmospheric chemistry, triggering unpredictable and non-equilibrium reactions, cyanide, CN, and organic. More worrying is the presence of hydrogen cyanide, HCN, the parent molecule of the CN radical that contributes to the green glow. As an interstellar messenger, Chapter 14, ATLAS transports complexes organic molecules, the basic building blocks of life, that will be launched into space. Exotic nickel. The detected nickel vapor, without its usual companion, iron, suggests the presence of volatile organometallic compounds that are chemically foreign to the inner solar system. ATLAS is traveling at a dizzying speed of 57 km/s relative to the orbit of Mars. This extreme speed is the critical factor that turns a simple vapor cloud into injection threat, atmospheric drag. As the comet's tail passes through the solar wind region near Mars, part of its cloud of gas and dust will be pulled into the planet's gravitational well. Even the thin Martian upper atmosphere will cause friction, slowing and trapping some of the interstellar material. Penetration depth. Particles traveling so fast possess immense kinetic energy. Unlike slow-moving dust, high-speed cometary gases and even microscopic ice grains can penetrate deeper in the rarefied atmosphere before being ionized or destroyed. The potential contamination of Mars' atmosphere and surface by these alien compounds represents a major nightmare for planetary protection, with implications for decades of scientific exploration. False positives. The main concern is forward contamination that could compromise the search for Martian indigenous life future. Rovers and sample return missions are designed to search for the precise chemical signatures of the building blocks of life, such as specific amino acids or organic polymers. If the Martian surface and subsurface are contaminated by interstellar organic matter using ATLAS, scientists could detect these crucial molecules, but they could not definitively determine Martian origin. Did these organic compounds form on Mars, supporting the hypothesis that there was past or present life on the red planet? Cosmic origin, or were they simply brought in by a massive transient comet? The ambiguity could sabotage billions of dollars of investment and delay confirmation of a true Martian biosphere by decades. Atmospheric acidification. The massive introduction of HCN, hydrogen cyanide, a highly toxic and reactive gas in the Martian upper atmosphere, could initiate complex photochemistry, potentially leading to the formation of corrosive compounds or an atmospheric state less conducive to future human life support systems. Surface sowing. While gases will eventually disperse, larger gases coated with organic matter, dust grains that slow down in the upper atmosphere, could eventually settle on the Martian surface. These grains, derived from a metal-poor extraterrestrial star system, could seed the Martian regolith with chemicals that interfere with in-situ resource utilization, KISARU, for human missions, or introduce complex organic structures that are neither natural to Mars nor immediately identifiable using terrestrial models. The flyover of ATLAS is not just an astronomical event. It is a chemical ambush, a unique opportunity to sample primordial galactic matter, but at the potential cost of permanently altering the pristine and scientifically invaluable environment of our nearest habitable neighbor. The approach of 3i ATLAS has triggered a deep philosophical crisis within the space community. The dilemma of planetary protection. This is the main ethical and scientific conflict over the preservation of the pristine nature of celestial bodies. And ATLAS represents an unprecedented threat because contamination would be extraterrestrial, uncontrollable, and that could permanently compromise the entire search for life on Mars. Planetary protection policy, governed internationally by the COSPAR Directors Space Research Committee, is designed to prevent forward contamination, the transport of viable microorganisms from Earth to other celestial bodies, to ensure the integrity of astrobiological research. Objective: Mars. Mars is a Category 4 mission target due to its potential to host extant living or extinct life and its history of liquid water, meaning missions like rovers undergo strict cleanup protocols to prevent Earth organisms from creating false positives that mimic Martian life. The ATLAS loophole. Current protocols focus entirely on man-made pollution, e.g. sterilization of spacecraft. ATLAS, however, represents high-speed, natural pollution from an extrasolar source, a scenario for which no international policy framework exists. The comet is releasing a massive, uncontrolled load of interstellar gases, heavy metals and complex organic molecules directly to the Martian neighborhood. The key dilemma is not safety. Since the comet is improbable to transport self-replicating organisms due to their long and cold interstellar journey, but above all, scientific ambiguity and telos of reference data. Irreversible corruption. If Atlas's huge cloud of CO2 and water vapor, saturated with HCN and alien hydrocarbons, settles on the Martian surface, especially in the protected zone, special regions, where groundwater may exist, that environment is irrevocably altered. The end of the search. Future missions designed to drill the surface for in situ resource utilization, ISRU, or to search for ancient life cannot be differentiated between life that may have originated on Mars and the organic soot deposited by Atlas. The detection of prebiotic molecules, a key step in astrobiology, becomes meaningless because the source of the material, Martian or interstellar, is impossible to definitively confirm. This impossibility of confirming the origin invalidates decades of expensive astrobiological data. The detection of nickel vapor without iron. This is a clear example of this dilemma. If the Martian atmosphere or regolith is found to contain high, localized concentrations of nickel, scientists must ask themselves, Martian geochemistry, is this a sign of an unusual and undiscovered Martian geological process? Interstellar pollution, or is it a molecular residue of the hypervolatile nickel tetracarbon, or what came out degassed from Atlas? The inability to distinguish between these possibilities, Mars's own history versus the history delivered by the comet, means that the scientific community may lose the ability to accurately read the history of the red planet. Beyond science, the dilemma forces us to confront our ethical duty in the cosmos, the moral right to interfere. Do we have the moral right to accept, even passively, the unsterilized contamination of a planet that could harbor unique life forms, even if the contamination is natural? The vast majority of the scientific community is of the opinion that the search for and preservation of possible extraterrestrial life is a supreme ethical duty. This outweighs other concerns, the consequence of ignorance. The most devastating consequence of Atlas's passage might not be a physical impact, but the creation of a permanent chemical veil that raises the fundamental question, did life ever arise on Mars? Irrefutable. The study of this fascinating 11 billion-year-old traveler comes into direct conflict with the obligation to preserve the 4.5 billion-year-old secrets of Mars. This makes the study coordinated by MAVEN and MRO not just a scientific gold rush, but a final, desperate attempt to quantify the chemical threat before the planetary protection line is permanently breached by a natural and unstoppable alien object. Although 3I Atlas is an unstable, high-speed visitor that poses potential risks to the Martian environment, you can rest assured that its trajectory through the solar system ensures an absolutely safe and non-threatening distance from Earth. The comet's trajectory, meticulously calculated by NASA and ESA, confirms that at no point does this interstellar object come remotely close to our planet. Closest distance. The closest point of approach between Tri-Atlas and the Earth is located in Friday, December 19, 2025. At that time, the comet will be approximately 1.8 astronomical units, AU, away. Concrete numbers. This translates to an astonishing distance of approximately 270 million kilometers, or 170 million miles. The safety margin. To put this into a reassuring perspective, 1.8 AU is approximately 8 times the distance between the Earth and the Sun. This is a colossal and comfortable cushion that places the comet firmly outside Earth's orbit, thus ensuring zero risk of impact or significant gravitational disturbances. The reason for this immense separation during their critical flyby period is a combination of orbital timing and alignment. Perihelion time. Atlas reaches its closest point to the Sun, perihelion, in October 29, 2025, passing just inside the orbit of Mars. Solar conjunction. Around this time, The comet is actually positioned in the opposite side of the Sun in relation to the Earth. This event, known as solar conjunction, means the Sun physically blocks our view of the comet during its brightest and most active phase. This alignment, while frustrating for ground-based observers, ensures that the comet's volatile outgassing and high-speed travel occur far from our planet. Mars's close shave. In contrast to its distant flyby of Earth, ATLAS performs a true close shave with Mars in October 3, 2025, arriving approximately 30 million kilometers from the Red Planet, Chapter 15. This proximity creates a unique opportunity for Mars orbiters, but poses no threat to Earthlings. The most profound conclusion to be drawn from these numbers is not the danger, but the peaceful coexistence the universe imposes. An object traveling from the galactic past at 58 km/s can glide through our cosmic neighborhood without even noticing our presence. This vast separation ensures that for humanity, 3I Atlas remains a fascinating silent messenger from the great void, posing only intellectual, not existential, questions. The trajectory of 3I Atlas is not a simple straight line. It is a complex, high-speed, hyperbolic curve dictated by the Sun's immense gravity. The comet's passage through the inner solar system, however, is a classic example of cosmic energy transfer, where their final escape velocity and direction will be subtly but permanently altered by the gravitational presence of the planets. This is the phenomenon of gravitational assist, or the slingshot effect, which acts on an interstellar body. Before discussing the planets, we must recognize that the Sun is the dominant gravitational influence in this entire maneuver. Incoming speed, Atlas entered the solar system with an excess hyperbolic velocity v of approximately 58 km/s, the velocity it had since deep interstellar space, maximum perihelion. As it falls toward the Sun, our star's gravity accelerates it enormously, causing its speed to reach a maximum of 68 km near its closest approach, perihelion 136 AU, by the end of October 2025, final escape velocity. After passing perihelion, the Sun's gravity will pull on the comet, slowing it down. Since its orbital energy is greater than its escape velocity, it will settle into a slightly altered final position, escape velocity v, which is its speed when it leaves the Sun's sphere of influence forever. The key question is, will v be exactly the same as v? In a closed two-body system, Sun and comet, the velocities would be almost identical. However, close flybys of Mars, Venus, and Jupiter introduce perturbations that subtly alter the comet's final, unbounded trajectory, the chain of approaches. Atlas's unnaturally aligned trajectory, Chapter 8, sequentially brings it close to the massive bodies of the inner solar system. Mars closest approach on October 3, 2025, 30 million km. Venus closest approach on November 3, 2025, 197 million km. Jupiter closest approach on March 16, 2026, 54 million km. Vector change. During these planetary encounters, the planet's gravitational field acts as a gravitational paddle. It does not significantly alter the comet's trajectory, speed, relative to the Sun while the comet is close to the planet, but the appearance of the comet changes subtly. Direction of travel, its velocity vector, relative to the Sun. Energy transfer. This slight change in direction causes a small exchange of orbital energy between the massive planet and the smaller comet. In the case of the comet, this means a small, permanent alteration of its final escape trajectory and its final escape velocity v. The most significant gravitational perturbation to Atlas's escape velocity will likely come from Jupiter on its way out of the solar system. Gravitational leverage. Jupiter, being the most massive planet, has the greatest ability to alter the comet's final escape trajectory. Although the closest approach to Jupiter, 54 million km, is greater than the Mars pass. Jupiter's immense mass gives it a much greater gravitational influence. Tyrrhochinus, final, Jupiter's gravitational field will impart a final, small directional kick to the comet, either slightly increasing its final escape velocity, v, or decreasing it, v, sending it on a subtly different path into the interstellar medium than it followed upon entry. The complete picture of 3I ATLAS, the journey, is therefore one of cosmic pinball without limits. It entered following a trajectory dictated by its former home, was accelerated and redirected by the Sun, subtly perturbed by the planets, and will ultimately exit our system with a slightly altered speed and a new trajectory, carrying the tiny but permanent gravitational imprint of its brief visit to the inner solar system. This final altered trajectory constitutes the object's definitive reception by our star system, a permanent record of its encounter. The most powerful lesson that the arrival of 3I ATLAS immediately dismantles the long-held assumption that interstellar visitors are a geological oddity. The detection of Oumuamua, 2I Borisov, and now 3I ATLAS in quick succession demonstrates that our solar system is not a quiet sanctuary, but a place of perpetual activity, galactic crossroads. And these ancient travelers are far more common than our previous technology could reveal. Before 2017, the known population of interstellar objects, ISOs, was zero. Now, we have 3 distinct macroscopic examples in less than a decade. This rapid succession of discoveries isn't a sudden influx. It's a reflection of our drastically improved detection capability. Demonstrating the long-theorized abundance of these ISOs, astrophysicists now agree that the Milky Way's local neighborhood is teeming with these cold, dark bodies. The estimated flow, current statistical models suggest that there are approximately 10,000 interstellar objects the size of Oumuamua, about 100 meters in diameter, passing within the orbit of Neptune. On a given day, this constant flow implies that several ISOs similar in size to Oumuamua, it will likely pass inside Earth's orbit every year. The tension of size. The discovery of 3I ATLAS, estimated to be between 5 and 10 kilometers wide, is the largest anomaly in the population census. Statistically, large objects are rarer than small ones. Models predicted that astronomers should have detected tens of thousands of Oumuamua-sized objects before encountering one as massive as 3I ATLAS. Its imminent arrival suggests 2 radical possibilities. Our models are fundamentally flawed. The size distribution of planetesimals ejected from other star systems may be dramatically skewed toward larger objects, defying standard fragmentation physics. Early ATLAS is a supertypical. Its detection is a fortuitous event of truly astronomical proportions, an event that occurs once every 10,000 years, or worse. The fact that these 3 visitors, arriving in just 8 years, have such different compositions and ages confirms that the ISO stream is sampling the entire 13.8 billion year history of the Milky Way. The era of interstellar discovery is just beginning. The ISO shortage to date has been a problem of instrumentation, not cosmic reality. The new era. The commissioning of the Vera C. Rubin Observatory and his legacy study of space and time, LSST, it will radically change the pace of discovery. The telescope is specifically designed to scan the entire southern sky every few nights with unprecedented depth and sensitivity. A new forecast. Models predict that the Rubin Observatory will likely detect dozens of new interstellar objects per year. Once fully operational, we will move from event-based astronomy, where every ISO is a surprise, to statistical astronomy, where the properties of the ISO population become a quantifiable field of study. The emerald glow of 3I ATLAS, it's the 3rd knock on our cosmic door. It serves as a potent reminder that the universe is actively sending us samples of its most ancient and exotic chemistry, and that the silence of the past is over. We are officially living in the era of regular interstellar visits. The arrival of 3I ATLAS coincided perfectly with the operational era of NASA and ESA's most powerful space observatories, making it the most analyzed interstellar object in history. The James Webb Space Telescope, JWST, and the Hubble Space Telescope, HST, have been essential, using their complementary optical and infrared views to reveal the comet's strange chemical core and the violent mechanics that drive its green glow. JWST, optimized for viewing on the near and mid-infrared spectrum, is uniquely equipped to penetrate the visible dust cloud and directly identify the frozen volatile gases that form the comet. His observations, specifically using the near-infrared spectrograph NIRSpec, produced the most striking chemical results. Direct detection. The main advance of JWST was the direct and robust detection of large amounts of gaseous carbon dioxide, CO2, at the exit of the coma. CO2 has a distinctive infrared signature in 4.3 microns that JWST can easily isolate, even at the great distance of Atlas, about 3.3 AU at the time of observation. The anomaly of proportion. The infrared spectrum confirmed the extreme CO2 to H2O ratio of approximately 8A1, a statistically unprecedented figure. This measurement directly proves that the comet is a body intrinsically rich in CO2, which drives its hyperactive behavior, and the outgassing paradox. Chapter 9. This chemical map of another star system is the first of its kind, and indicates to scientists that Atlas's original stellar disk was chemically biased toward CO2. Other organic products, JWST also detected carbon monoxide, CO, and traces of carbonyl sulfide, OCS, along with water ice and water vapor, H2O. This set of volatiles provides a complete picture of the ancient chemistry trapped in the cold that now bubbles within the core. While JWST cannot directly measure the diatomic carbon, C2, that causes visible green light, which occurs in the optical spectrum, its infrared data explain the fountain from green, the rapid and intense sublimation of CO2-rich ices, which rapidly releases the organic parent molecules, HCN, C2 precursors, needed to create the green C2 radical in the inner coma. Hubble Space Telescope, HST, with its superior angular resolution in visible light, was crucial for observing the shape and kinematics of the coma dust. Teardrop feather, HST images captured a distinctive image, teardrop-shaped powder cocoon, which was breaking away from the solid, invisible core. The brightest part of this fan-shaped column was directed towards the sun, instead of forming a long tail behind the comet. Dust ejection. This morphology confirmed the rapid and localized jet activity on the sun-facing side of the core. Analysis of this plume allowed scientists to determine that the dust was being ejected at a low velocity, just a few meters per second, and provided the firmest constraint on the core's physical size, setting an upper limit of 5.6 kilometers in diameter. Combining the JWST chemical model, what the comet is made of, with the morphological map of the HST, how the comet is ejected, astronomers have constructed the most complete picture to date of this 11 billion-year-old Voyager. Twin space telescopes have confirmed the comet's volatile, chaotic, and chemically anomalous nature, cementing its role as a revolutionary, if deeply enigmatic, artifact of galactic history. Visual analysis of the material flowing from 3I ATLAS provided essential clues about the inner workings of this interstellar object. The patterns of its visible cometary jets. They are not random explosions, but rather structured columns that serve as a direct diagnosis of the core's rotational state, its thermal response, and the hazards, non-uniform sublimation that threatens to tear it apart. Observations by the Hubble Space Telescope, HST, and ground-based facilities captured the comet's coma developing into a distinctive fan-shaped plume, or a wide extension towards the Sun rather than a perfectly spherical gas cloud. Directional flow. This form confirms that the vaporization of ice is highly anisotropic, is overwhelmingly concentrated on the side of the core currently facing the Sun. The Sun's radiation is heating a specific area of the ancient, dark crust, and the underlying volatile ice is preferentially escaping through that localized region. The anticola. This non-uniform outgassing also explains the unusual phenomenon of a weak anticolar sunward elongation. Chapter 10. The larger gas and ice grains ejected toward the Sun are heavy enough that the weak solar radiation pressure does not immediately push them back, forming a conventional tail. Instead, they form acolum directed towards the Sun before they are completely sublimated. A high-impulse, directed outflow signal. The jets are not only directed, but are modulated by the comet's rotation, revealing the dynamic complexity of the nucleus. Rotation period. Careful photometric modeling of the coma's light variations determined that the nucleus rotates with a period of approximately 16.16 hours. Active zones. The way the brightness fluctuates during this rotation, which shows multiple peaks, harmonics. Rather than a simple single peak, it suggests that the comet's activity is dominated by 2 or 3 highly concentrated active points, or vents, as the core rotates. Each jet turns toward direct sunlight, CO2 sublimation momentarily accelerates, and a localized plume of glowing material expands outward, causing the observed increase in brightness. The rotation period is essentially the frequency of these thermal pulses. Jets are the physical realization of the theory non-gravitational force acting on the comet. The rocket effect. The great momentum of the vaporized gas and entrained dust acts like a constantly firing rocket engine. Because the jets are asymmetric, located on the day side, they impart a slight constant thrust or torque on the core. Mass versus thrust. Cometry scientists use the measured gas outflow, the thrust, determined by the JWST, CO2 rate, and the observed deviation from a gravitational trajectory, the acceleration, to calculate the nucleus's mass. The fact that Atlas's trajectory is so stable, despite its intense jet activity, it leads us directly to the conclusion that its nucleus must be anomalously massive, 33 billion tons, to resist the thrust of these powerful CO2 jets. Unusual exit. On the contrary, the observed slowness of the ejected dust grains, estimated at only a few meters per second, suggests a weak coupling between the vaporizing CO2 gas and the entrained solid material. This weak coupling is another sign of the comet's strange, possibly alien internal structure, as the gas jets are powerful in terms of mass flow, but surprisingly gentle in terms of velocity. The cometary jets of 3I ATLAS, they're more than just a beautiful sight. They're the volatile exhaust of an ancient cosmic machine, telling a story of uneven material, high internal pressure, and unexpected mass that challenges decades of comet modeling. The myriad of puzzling properties it displays, i.e. Atlas, its extreme age, its high speed, its anomalous mass, and its strange nickel and CO2 chemistry cannot be reconciled within the traditional framework core accretion model of planetary formation. The comet demands a radical new hypothesis that redefines how icy bodies form in the vast and ancient realms of the galaxy. The canonical core accretion model suggests that planets and planetesimals form slowly, piece by piece, from microscopic dust and gas in a localized stellar disk. the ATLAS profile invalidates key assumptions of this model. The CO2 paradox. The old model assumes that water, H2O, should predominate in comets, since water ice is the most common volatile. ATLAS's 8.1 CO2-H2O ratio is scientifically inexplicable by standard condensation and accretion processes in a solar-like disk. It implies either massive CO2 enrichment or a drastic depletion of water in its star system. The challenge of the metal pore. ATLAS's high-speed trajectory suggests formation in the was pore in metals when heavy elements were scarce. The old model states that low metallicity should lead to inefficient planet formation. However, ATLAS is massive, which implies efficient formation, and chemically complex, containing exotic nickel. The mere existence of such a large, pristine, and complex object from this age challenges the long-accepted chronology of when the cosmic starter kit was amassed. ATLAS's anomalies, particularly its size and chemical imbalance, have driven the interstellar planetary seeding hypothesis, which changes the script on the rate at which planets can form. Current simulations for the core accretion model have difficulties with the barrier. The size of 1 meter dust particles grow to about a meter, but at that size they tend to bounce off each other or fragment rather than coalesce to form kilometer-sized planetesimals, ATLAS as a ready-to-use seed. The new model proposes that large interstellar objects such as 3I ATLAS, BT 5 km, and Oumuamua 100 mm are constantly captured by the dense, dusty protoplanetary disks around young stars. These ISOs are prepared seeds that they have already solved the problem of the subway barrier, driving accumulation. Once captured, the ISO provides a massive core which acts as a gravitational anchor, immediately beginning to sweep the surrounding gas and dust away from the stellar disk. This dramatically accelerates the accretion process. This seeding mechanism elegantly solves a persistent problem, particularly Forgus giant formation around larger, sun-like stars. Short disk length, protoplanetary disks around massive stars typically disperse in just 1 to 3 million years. This time is often too short for a gas giant to form its massive rocky core through slow, traditional accretion before the gaseous envelope disappears. The aliens start by capturing an interstellar seed. The star's disk obtains a head start. The core of the giant planet can form before the gas dissipates, providing a rapid pathway for the growth of massive planets within the short period available. This helps explain why large gas giants are observed to be more common around larger stars. These stars are also more efficient in gravitational capture high-speed ISO seeds like ATLAS. The detection of nickel without iron. This requires a radical review of the formation of refractory, rocky metallic materials in space, formation in stellar winds. Some models suggest that ATLAS may have formed in the dusty wind emanating from an asymptotic giant branch, AGB star, a star nearing the end of its life. AGB stars produce unique chemical characteristics, including elements of the S process, which could lead to the formation of highly volatile compounds such as nickel tetracarbonyl, NeTCO4, chemical uncoupling. This volatile nickel compound would condense and freeze at different temperatures and pressures than traditional iron silicates. Chemical dissociation during formation, where metals are separated by volatility rather than simple density. This would explain why ATLAS is releasing nickel vapor now, while the heavier, less volatile iron remains trapped deep within the core. The interstellar visitor is not just a comet, but a living laboratory of extraterrestrial physics, demonstrating the galaxy's chaotic yet efficient ability to create the most essential building blocks of planetary systems at any time and in any chemical environment. The quest to precisely date the formation of 3I ATLAS relies on a far more subtle technique than tracking its immense speed, analyzing its carbon isotopes, specifically the relationship between carbon-12 to 12C, a carbon, 13C. This isotopic ratio acts as a cosmic clock, revealing the chemical heritage of its long-dead parent star. Isotopes are atoms of the same element that contain different numbers of neutrons. For carbon, the two stable isotopes are carbon-12, 12C, the common form, produced mainly during the helium-burning massive star phase, carbon-13, 13C, the rarest form, produced mainly through the CNO, cycle carbon, nitrogen, oxygen, cycle inside stars. The 12C-13C ratio in the gas cloud of any stellar system acts as a direct indicator of the degree to which that cloud has been enriched by subsequent generations of stellar material. Would be the reference point of the solar system in the young, thin, chemically evolved disk of the Milky Way where our Sun formed. The ratio is relatively low, about 90 parts of C12 for every part of C13. This indicates that multiple generations of stars have lived and died, enriching the environment with both isotopes. Initial spectroscopic analysis of the volatile coma from 3, ATLAS provided an intriguing, if complicated, result. The carbon isotope ratio was measured to be broadly similar to the relationship of the solar system. At first glance, this similarity might suggest that ATLAS isn't as old as its extreme speed implies. However, scientists quickly realized the complexity: surface contamination. The coma gas we are measuring is only of the outermost and most volatile layer of the comet, which has been exposed to the interstellar medium, ISM, for billions of years. During this time, the comet has passed through various interstellar clouds and stellar environments. Chapter 7. Likely absorbing or being chemically altered by the ambient ISM-docked galactic recycling. The current ISM is chemically well mixed and has a carbon isotope ratio similar to that of our Sun. Therefore, the ratio we measured may reflect the relatively recent and well-mixed material of the modern ISM, rather than the true one, pristine proportion from the deep, ancient core of the comet. The real challenge of the age of ATLAS, up to 11 billion years, is linked to its probable origin in the thick metal-poor disk. This connection predicts a specific outcome for its core relationship that might yet be discovered. Expected signature: extremely old, ultra-metal-poor stars often show 12C, 13C ratios that are significantly higher, more dominated by C12, than the value for the solar system, because they formed from gas contaminated only by the first star's population, which only produced C12 in their nuclei, unlocking the core. If future high-resolution spectroscopy, perhaps from a long-term follow-up by JWST or a dedicated mission, can penetrate deeper into the coma as the comet loses more mass, it could reveal the true nucleus, higher isotopic ratio. This would provide definitive chemical proof that ATLAS is indeed an 11 billion-year-old relic, a chemical timestamp from the dawn of galactic evolution. For now, the ambiguity of the carbon ratio means the controversy continues, but it drives an urgent need for precise measurements of other isotopes, such as oxygen, O18, O16, which may provide a clearer and deeper insight into the comet's true age. The emerald glow of 3, ATLAS is a beautiful visible sign of its extraterrestrial nature, but for astrobiologists it is the toxic and invisible chemical substances that the green glow often masks that pose the greatest scientific and environmental concern. The detection of these compounds highlights the comet's dark side, a cargo of lethal materials crucial to the origin of life. The molecule directly responsible for the spectacular green light is diatomic carbon, C2, which forms when ultraviolet light from the Sun breaks apart larger parent molecules. One of the most abundant and important of these parent molecules is hydrogen cyanide, HCN. Spectral challenge. In the immediate vicinity of the core, HCN gas is actively sublimating, but its spectroscopic signature is often difficult to isolate because the intense visible light emitted by the resulting C2 and CN radicals dominates the spectrum. The presence of the green C2 glow is therefore masks the initial release of HCN, creating a complex analytical puzzle. The CN proxy, astronomers usually detect HCN indirectly by observing its photodissociation product, the highly fluorescent cyanogenate radical CN, which is visible in the blue-green part of the spectrum. The detection of NC production rates on the rise-in, 3I ATLAS on the VLT, it is the alarm signal. It confirms that a massive and unquantified supply of HCN is boiling from the old core. Hydrogen cyanide is famous for two paradoxical reasons that directly affect the 3I ATLAS mission. Deep toxicity, HCN, is the extremely toxic compound on Earth. It acts as a cellular asphyxiant, binding to the enzymes needed to use oxygen in metabolism, and can cause death within minutes, even at low concentrations. This is the dark side the comet's tail, the reason Halley's Comet caused a brief panic in 1910 when its CN signal was first detected. The Atlas tail, if the Earth were to pass through it, wouldn't be a threat due to the extreme rarity, low density, of gas in space. But concentration, being ejected by the comet, is immense, the foundation of life. On the contrary, astrobiologists consider HCN to be one of the most critical molecules. Top rebiotic chemistry experiments show that HCN reacts spontaneously with itself and with water to form sugars, amino acids, and the fundamental nucleobases such as adenine and xanthine that make up DNA and RNA. The abundance of HCN at 3I ATLAS means the comet is simultaneously releasing a molecular poison and exact recipe. Lifelong. Atlas's inventory of toxic compounds extends beyond the familiar, underscoring its unique makeup. Volatile nickel, Ni-Kia Tisi-Forchor. The inexplicable presence of ironless nickel vaporis, strongly suggestive of nickel tetracarbonyl, NiCO4. This is a volatile and highly toxic organometallic compound commonly used in industrial nickel refining on Earth, but rarely observed in natural cometary environments. Its sublimation is extremely pronounced upon solar heating, R9, indicating a source structure and chemical processing completely alien to our expectations. Increased risk of contamination. The presence of these non-aqueous alien volatile species, CO2, HCN, Ni compounds, amplifies the planetary protection dilemma, Chapter 18. Any interstellar dust or gas injected into the Martian atmosphere by Atlas during the flyby is a dose of extraterrestrial chemical precursors which could drive the evolution of life on Mars or completely compromise the future search for indigenous Martian biosignatures. The green glow is beautiful, but it's a distraction. The most profound and scientifically urgent story of 3I ATLAS is the volatile, toxic, and complex chemistry that boils from its ancient core, a cargo of poison and the potential model for the emergence of life throughout the galaxy. The journey of 3I ATLAS, it's not just a hyperbolic plunge through our solar system. It's a meticulously choreographed journey, from 7 to 11 billion year galactic journey, a profound journey, through the immense scale of the Milky Way that eventually intersects with the local cosmic path of the Sun. Understanding where this object originated requires visualizing its path through the spiral structure of our galaxy. Kinematic analysis of Atlas's high-velocity V58 km/s and unique trajectory provides the strongest evidence for its origin. The Milky Way, thick disk, the galactic direction. The Milky Way is composed of several major stellar populations, defined by their age and metallicity, abundance of heavy elements. The thin disk, where our Sun planets and younger stars reside, is chemically rich and moves cohesively. Thick Dissat is populated by older, metal-poor stars that formed early in the history of the galaxy. The steep angle. If we trace the trajectory of Atlas backwards, we will see that its movement has a tall vertical component, the z-axis, meaning that it wobbles significantly up and down above and below the plane of the Milky Way. This large excursion of the z-axis is a signature of the oldest and most dynamically heated stars that make up the thick disk population, confirming that Atlas is a relic from the early days of the galaxy, the age of the Elder. This association suggests that Atlas could be between 7 and 11 billion years old and contain pristine material from a star system that was born long before the solar nebula collapsed. For billions of years, Atlas has followed a vast and eccentric orbit around the center of the Milky Way, passing through immense cosmic structures. Spiral arm passage. The journey has taken him through numerous spiral arms, the dense, star-forming regions that spiral out from the galactic core. Each spiral arm is a vast cloud of gas, dust, and young stars. Each passage exposes the comet to different gravitational fields and different levels of cosmic rays. Gravitational jerk. Although Atlas's current trajectory shows that its motion has not been significantly altered by any close stellar passages in the past few million years, its immense hyperbolic velocity is the cumulative result of billions of years of gravitational shocks by large objects, passing stars, giant molecular clouds, and remnants of stellar nurseries across the galaxy. These small, constant impulses have accelerated its speed, giving it the extreme velocity it exhibits today. Current address: when discovered, Atlas appeared to be traveling in the direction of the constellation Sagittarius, toward the central bulge of the Milky Way. However, its entry velocity is so high that it simply passes through the Sun's local environment, using the Sun's gravity as a boost to exit the inner system. The strangest thing is the final stage of its journey, its improbable trajectory near the ecliptic plane. Retrograde, but flat. Atlas is traveling in a retrograde orbit, opposite to the motion of the planets, but it is unnatural aligned with the plane in which our solar system is located. This alignment, statistically estimated at a probability of 1 in a million for the random arrival of an ISO, has become the most controversial. The final act. This unlikely flat trajectory, whether natural or technological, is the only reason the comet makes a sequential pass close enough to Mars, Venus, and Jupiter to be fully observed. The ancient messenger offers us a clear perspective on its history as it executes its final high-speed exit from the Sun's immediate realm. Atlas is truly a journey into the deep past, offering a physical view of a vast and dynamic galaxy that has been creating and ejecting planetary building blocks since its earliest days. As 3I Atlas passes its peak activity near the Sun and begins its long, final retreat into the interstellar void, its lasting signature will remain in the form of a cloud of microscopic dust, exotic molecules, and possible debris. Afterglow, it will leave a lasting, if subtle, chemical and physical legacy in the inner solar system, which future space missions will need to take into account. The comet's intense sublimation, driven by CO2, has been shedding material at a rate of approximately 150 kilograms per second for months. This vast outflow generates a huge cloud of dust and gas that is left behind, forming a subtle but sweeping stream in the inner solar system, confirmation of solar radiation. Because Atlas moves on a hyperbolic, unbounded trajectory, the dust and gas it releases do not settle into a stable, closed orbit like the debris from a solar system comet. Instead, the material is immediately subjected to two main forces: solar wind. The charged gas components, CO2, CN ions, nickel vapor, are dragged away almost instantaneously, forming the ion tail, which dissipates in the solar wind. Radiation pressure. Microscopic dust particles are blown away by the force of sunlight, creating a fan-like tail that trails behind the comet's nucleus. The heaviest and largest dust grains remain closer to the comet's orbit, while the lighter and smaller ones are ejected to great distances, a new component of the zodiacal cloud. Over time, this dust will disperse into the inner solar system, contributing a temporary exotic component to the zodiacal cloud, the faint, diffuse cloud of dust that orbits the Sun and causes the false dawn light phenomenon. This dust is unique because it carries the extraterrestrial chemical signature from the thick, metal-poor disk, including the elusive organic compounds rich in Ni and CO2. The comet's long-term legacy poses a very real, though low probability, risk to future missions due to the speed of the remaining debris. Risk of fragmentation. If, as feared, Atlas's large, unstable nucleus fragments near perihelion, it would release a cloud of centimeter and millimeter scale fragments along its trajectory. These fragments, traveling at the comet's extreme hyperbolic speed, more than 60 kilometers in relation to the Sun, they would transform into extremely high-speed micrometeoroids. Orbital intersection, any spacecraft, satellite or future human habitat intersecting this stream of scattered debris, especially in Mars orbit or on a transfer trajectory between Earth and Mars, would face a hypervelocity impact risk significantly greater than that posed by the much slower, gravitationally bound micrometeoroids of the solar system. Even a dust grain impacting at 60 kilometers can puncture critical components, degrade solar panels, or threaten a pressurized habitat. Assessing this risk is essential for missions planned for the next decade. The dilemma of planetary protection persists long-term. Even after the initial coma disperses, the extraterrestrial organic material and nickel dust that was injected into the atmosphere and surface of Mars during the close flyby will remain. Permanent baseline shift. This material will establish a permanent layer of contamination on Mars, ensuring that any future scientific experiments looking for indigenous Martian biochemistry will have to account for the presence of interstellar organic false positives. A chemical foundation of the red planet is irrevocably altered by the passage of this ancient cosmic messenger. The green flash of 3I Atlas will be fleeting, but the remnants it leaves behind, a diffuse, high-speed stream of ancient galactic particles, will remain a subtle but permanent hazard and a profound chemical enigma woven into the fabric of the inner solar system. The final chapter of the 3I Atlas saga is its inevitable departure. After venturing into our inner solar system to deliver its ancient, glittering cargo of alien chemistry, the hyperdrive courier now finds itself on a guaranteed path of no return to the cold, silent depths of the galaxy, a journey to extinction. The comet's fate is sealed by its extreme orbital properties, an eccentricity, E6.14, much greater than the escape velocity threshold. Perihelion, slingshot. After its closest approach to Mars, October 3, 2025, and the Sun, perihelion, on October 29, 2025, at 1:36 AU, the Sun's massive gravitational field will accelerate it one last time, acting as a cosmic slingshot. This maneuver, combined with subtle perturbations from Jupiter in March 2026, will send it rapidly outward. The final destination, unlike the comets in our Oort cloud, which remain gravitationally bound to the Sun, 3I Atlas will retain its extreme speed, completely leaving the sphere of influence of the solar system. Its trajectory will take it back to the interstellar medium, ISM, never to return. It won't join the Oort cloud of a distant star. It's a true galactic wanderer, final speed. As it leaves our solar system, Its velocity will stabilize again at its hyperbolic excess velocity of 58 km/s, and it will continue its colossal elliptical orbit around the galactic center. Chapter 27. I-Atlas's brilliance is transient and is fueled solely by the sun's heat. As the comet moves away, its visible life in our sky will slowly fade. The observable window closes. The comet will be briefly hidden from Earth in late October or early November during solar conjunction, but will reappear in December. Its closest point to Earth, by 270 million km, will be around December 19, 2025, providing a final window for observations by important facilities such as the James Webb Space Telescope and the Vera C. Rubin Observatory. The end of the green glow. As its heliocentric distance increases, the solar heat falling on the core will rapidly decrease. CO2 outgassing, the high-pressure engine that fueled its extreme activity and produced C2's bright green coma, will cease as temperatures drop below CO2's sublimation point. The visible green glow fade away completely. The dark shell, the core, will regress to a state of cold storage. Chapter 7. The porous surface layers, having lost massive amounts of volatile CO2 and H2O, will collapse, leaving behind a dusty, darker, and partially depleted bark. This new mantle will once again seal the remaining ancient ices of the core, locking the comet into a billion-year hibernation until its distant galactic orbit can one day bring it close to another star. The final image from 3I Atlas will be one of profound loneliness. A dark rock, a kilometer in size, barely visible to the most powerful instruments, silently accelerating into the vast cosmic night, bearing the permanent scars of its brief and chaotic encounter with our sun. The secrets held in that emerald glow, a history written in ice and organic dust from a time before Earth existed, will keep astronomers busy for generations. But for now, its urgent message fades as it recedes, leaving us to wonder how wrong our history books really were. If this cosmic journey helped you reach the farthest corners of the universe, ACES video subscribe a hollow Earth for greater relaxation in deep space, and comment below. What do you think is the biggest secret of the green comet? Sleep well, traveler.